Yeah. Okay, thanks. So we'll continue. So during the first two lectures, we already introduced the detailed formula, the technical styles, the technical details of the EPL spin-form model. And now this lecture is mainly examples and how to use this code, or how to write this code. So the plans is listed as the following. So first, I'll show you how to construct boundary data and solutions. So from the last lecture, we already know that the real critical point of the EPL model, the EPL action, is correspond to for simplex. So this corresponding, so the construction of the boundary data and the solutions is somehow geometrically correspond to the for simplex, all the things relate to for simplex. And then we write the action, and then we can verify our result by the variational principle, and we can also derive the Hessian, which is useful when you want to do the saddle pointer approximation. You know the saddle pointer approximation is the critical action, which is the action at the critical point, and also you have the square root of 2 pi over the determinant of the Hessian. That is needed for the asymptotic expansion of the amplitude. And on the third one, I'll introduce the SL form next code and how to use it. First thing is how to install it. I know it's already very complicated as it's C code. And the first is an example of the Loops' symbols. We use every function as an example, and we show how to use the micro Monte Carlo method to sampling the Loops symbol of the every function to get the observable expectancy values. So I hope I have time to do all the things. So maybe some part will be fast, but all the code will be available later on the school's resources webpage. So you can find them and you can try yourself. Okay. So then I think I'll switch to my computer. Good. Thanks. Okay. So the first thing is boundary data. So this is more or less to construct the coherent state we needed to construct the coherent state for the SL2C form to have a quantum evaluation, but also have the semi-classical action. So it's a Python code. Before we go into the details of the code, let's try to see how we construct the boundary data. So last time, we already see that the real critical points, they correspond to four simplices. And we have the two equations of motion on each four simplex. Let's stay on each four simplex. We don't do four simplices. So for each four simplex, we have this one, which is the parallel transport. And we have this one, which is the closure. And here B is the bar vector. It's an element of the algebra of the SL2C, or SO13 if you want. And this group element G is SL2C group elements. So we have these two equations. And basically what we want to solve is the group element. The reason is in each four simplex, this condition become a constraint on the boundary data. So it's a condition on the boundary data. Basically, BRG is the boundary data we need to give. So finding the boundary data correspond to finding the corresponding B, and then we decompose B. Remember last time we already said this B is actually given by the coherent state labels, each coset corresponding to a 3D normal of your triangles of the tetrahedron. So given B is the same as given C, which is the coherent state label of the SU2 coherent state. So this is the boundary. That's why we call it how to build the boundary data. And also we have the solution of the critical equation is now given by these SL2C group elements. Now the task is how to build these two data from a geometry. One thing is when we give the geometry, we give the whole for simplex. It's a 4D object. At the beginning, it's not very obvious how to get this boundary data, which is only a 3D object. So we need to project it to its own reference frame from the 4D to the 3D subspace. That's the main task. And this rotation from the original 4D reference frame to the 3D reference frame is exactly given by these group elements. So these two are correlated. Now we start with the geometry of a for simplex. So you already heard this several times during Francesca's lecture, Bianca's lecture, and also Qiao Yin's lecture. So a for simplex is determined by 5 points in a 4-dimensional space. So we call it P1 to P5. And it's a flat for simplex, it's piecewise flat. So that's a triangulation. We use piecewise flat for simplex to triangle our 4-dimensional manifold. And equivalently, we already said last time, it can also be determined by 5 normalized 4D normals. So other 5 points of 5 normalized normals. Of course, this is normalized, so the for simplex is determined up to an overall scaling. And then when we fix the area, everything is fixed. Normals I don't need to explain. So normals is the normal to all the edge vectors, which is orthogonal to it. So it can be written like this. So the normal contracted with the edge vectors, which is so the RGK are different labels. That means for the normal I equal to 1, it's determined. It's the normal of the tetrahedron determined by 2, 3, 4, 5 points. So 4 points determine a tetrahedron. Like 3 points determine a triangle, 4 points determine a tetrahedron, 5 points is for simplex. Okay. And this boundary of for simplex is just given by you cut the normals with hypersurfaces. That's why given 5 normals, you also give the for simplex up to a scaling by cutting the orthogonal hypersurface. And now we also know that we have 10 triangles in each for simplex. So we have for each triangle, we have a normalized geometric bivector. And this geometric bivector is given by a tensor product between the normal I and normal J. That means this bivector describing the 2 tetrahedrons which determined by Ni and Nj. So Ni and Aj corresponding, so they have the tetrahedrons in each orthogonal subspace. So this tetrahedron glued together, they share a triangle. And this is the bivector for that triangle. So yeah, do you understand? If you don't understand, I can draw a diagram. Yeah, if it's okay, I can continue. So, okay. And this is bivector, and you know we also define the inner product of the bivector, or the normalization of the bivector, which is 1/2 the contraction of the bivector itself. So it's Minkowski signature. So we use eta to do the contraction. So this capital R and capital J are space-time, the eta, the Minkowski index, if you want, from 0 to 3. And using this language, we can solve the parallel transport equation, which is this one, transform it into a spin one, what we call spin 1 representation, basically, is a representation in 4D. And this is nothing else, tells you that the geometric bivector is the transformation using the SO1 group element of the 3D, the bivector in the 3D space. So this is the boost of the original 3D bivector to its 4D version. And this 4D version is determined by our points in the 4D space. one thing is now we introduce a kappa. This kappa is introduced according to the graph, the directed links, if you want. We already discussed it last time. One more thing is I directly write is SO13 plus. Why is SO13 plus? Because we know SL2C is a double cover, but we also have a gauge transformation of the. You can also see this from the equation motion. If I add a plus or minus sign, it doesn't change anything. So this actually is a discrete gauge transformation can be used to fix the lift. So we can always lift it. And we chose SO13 such that. And finally, as I said, this BRJ without V is a 3D, is a vector for the 3D subspace, for more or less. And it can be constructed by a normal vector and multiply the 3D vector. And this normal vector is a standard reference vector. So it's 1, 0, 0, 0 for EPRL because we use SU2 gauge fixing. So U0 is always the time along the time direction. So this is the gauge fixing. And all the tetrahedrons are space-like. This is the EPRL. And this can be extended in the Kurandi Habida extension, but here we will stay in EPRL for simplicity. And finally, when we have this lambda, the normals is nothing else but the boost of the reference normal to its 4D version. And more or less, it means when we know normals, we can find a set of SO1 through group elements that solves the parallel transport equation. But now this is spin 1/2. This is not 4D, this is 2D. So this is a projection, a map from a solution from SO13 into SR2C. And this is fixed already by choosing the gauge. So basically, when we obtain a SO13 solution, we also obtain the SR2C solution, and this solves the parallel transport equation and fix everything. So these are all the facts we know. And our task is really when we give, for example, 5 points to build everything. I mean, when one have many methods to build following this fact, basically the construction procedure is the following. So given 5 points, we first determine 5 normalized normals. And when we have the 5 normalized normals, we can obtain the group element from the vectors. We know how to boost the vector to another one. And from here, we can obtain the group elements. And from the group element, we can reconstruct we can boost it back to its own reference frame, such that from the 4D vector, we project it into the 3D subspace. And finally, from this 3D vector, we obtain the Cauchy, which is our boundary data. That's the procedure. There are many methods, but one good method is to avoid anything that we need to solve an equation. Of course, for example, when we build the normals from edges, because 5 points basically gives you 10 edge vectors. The easiest way to build the normals is to solve an equation that the normals is orthogonal to the edge vector you have. But we would like to avoid anything that we need to solve equations, because usually this is hard in numerical calculations. We need algebraic system otherwise. So this is a special method and to avoid to use any solving methods. So we directly use elementary linear algebra operations to do this for procedure. So I will sketch how to obtain this thing. First is how to obtain the normals. So one naive thing is we can inverse, if we can inverse a matrix, somehow we get the normals. But the problem is now this matrix, if I write this P1, P2, P3, P4, P5 is vectors, each column is a vector, so this forms a 4x5 matrix. So we don't know how to do the inverse. But there is a good way is we introduce an auxiliary dimension. So we form, so instead of 4x5, we form a 5 cross 5 by adding 1 to the last row. This we obtain a 5 cross 5, and also you can show that it is invertible if these PRs are linearly independent. So basically, they span the 4D, space instead of a 3D subspace. So when it's not degenerate, this M matrix, which is we add a row which is 1 into the original point, is not degenerate, and it has the inverse. And now we find the inverse. This is just a linear algebra operation. And what is the meaning of this inverse? And this inverse is nothing else. If I write the inverse, is a covector in this 5-dimensional space that contracted with this yi is delta rj. So this is we find the co-basis of the yi as the basis. And now this means from this relation, this means that this covector contracted with edge vector. So if we if one y minus another y, we cancel the extra dimension we have. It automatically becomes 0. So this is actually tells you that this y hat I is a covector to your edge vector. Of course, you have extra dimension. So but this extra dimension is trivial because its 5 index is 0. So from here, you automatically obtain the conormal of your edge vector. If you just ignore the 5 dimension you added. So this is basically how we obtain the normal vector from here. So we write the inverse matrix of this 5 cross 5 matrix. And then we just taken its 1 to 4 Coulomb. We obtain again the covector as 5 cross 4 matrix. Of course, it's a covector, so to bring it as a vector, we just multiply the matrix we have. So in this way, we obtain the normal vector. And these are only elementary operations. We don't use any solve or algebraic equations. OK, area is trivial. I don't want to talk about it. It's just because we have the edge vector, you can obtain the area directly using the standard triangle, how to obtain the area of a triangle with the edge vectors. And now we go to the group elements. So we know how to obtain the group element is to solve this equation. But if we are familiar with any representation theory or SU2, it's a similar thing happens. Here is, of course, SO13. The solution, which basically the both group elements that both 1 N1 to N2 is given just by the exponential multiply the dihedral angle, and then with the B matrix, which is the bivector. And this bivector is just defined by the N1 wedge N2. So this is the group elements that both N1 to N2 up to the transformations that transform the subspace of N2 or N1. And this theta is nothing else but dihedral angle between A1 and N2. Here, remember, the Lorentzian group only boasts the SO13 plus, will only boast the same vector in the same quadrants. Namely, for example, if they are both time-like, they need to have the same T elements. So this basically gives you the SO13 plus elements. And then how to project it into the spin 1/2, which is SL2C. And we can basically map this bivector, which is the SO13 Lie algebra, to the SL2C Lie algebra. And by mapping the bivector, which is basically the generators, we automatically map. It's also induce a map for the group elements as a 1-parameter family of the exponential map. So this is given by map the SO13 Lie algebra. Here I just define what is KR and GR. You can read it afterwards. And map to the spin 1/2 representation, which is given by the polymetrics. And using this map, we directly obtain the SL2C group elements when we have the dihedral angle, and also the corresponding SO13 bivector, which is the 4D bivector. And finally, we obtain the boundary bivector, which we now transform back the 4D bivector into the 3D version. Why it's 3D version? Because you can show that This is nothing else but is the SU2 rotation of sigma 3, which is Ki. And then we can get a 3D vector by just tracing out the value of this Bij with Ki. So here we obtain directly a 3D vector, and then the theta and phi, which determine this cosine or determine the coherent state labels. So theta and phi is just the angle of our normal vector, so it's just the spherical symmetric coordinates. And this spherical symmetric coordinate transform to the cosine, which is the coherent state label by the standard way. And you can see this is a spinor, which is normalized to be 1 in SU2 groups. So this is basically how to construct the boundary data for single four simplex. And if we have multiple four simplices, we can construct it for each four simplex. And then we identify the gluing. Identify the gluing means we make sure that for the glued tetrahedron, the Bij is the same. That's the only thing we need to do. But this can be done easily by transforming, because when we determine everything, there is always the extra SU2 gauge transformation for the SU2 rotation for the subspace. We can multiply it to finally identify everything. So that's all the things we need to do. I have implement all these ideas with the Python code. If you are interested, you can also implement it by yourself, use any code you want. Here is just to show this is very easy. I can just run this. So I define all the things I need. Sorry, let's run from the beginning. So I only need minimal packages, SymPy and NumPy. The others we don't need. So SymPy is a symbolic package for Python. So here I keep everything symbolic as much as possible until I cannot calculate. So we can make sure we have arbitrary position we want. Here I just define, as I said, all the generators in spin 1 and spin 1/2. And then I define what I said, the bivectors, the whole duality, the inner product of the bivectors, and how to transform, how to map the spin 1 bivector to spin 1/2 bivector. So these are some elementary functions, and then we define the dihedral angle, and we can directly get the group elements according to what we just said. So we have everything. And the dihedral angle is only a function of two normals, the reference normal and the normal we obtain. So everything is very easy. You can just run it yourself. I can just do a test run if you want. And this is how to obtain the normals. Yeah, so there is a function which basically calculates everything, summarize everything for you when we give 5 points. This is a test. So we give 5 points, and this 5 point is such that we have an area which is constant. So how it built is in the following way. So we have we have an equilateral tetrahedron such that the area is 5. And then we found another point such that all the remaining area of the triangle is 2. So remember in the spin form, what happens finally in the asymptotics from the action is the spin. Spin looks like the area. Oh, of course, you need to multiply the emergence parameter, but that's a constant. That's why here we always, we prefer the integer areas. So this is just an example to have integer areas and to build the point which have the integer areas. Of course, this calculation of the area is trivial. This is the area matrix of our tetrahedron. So each row tells you which tetrahedron you are. Each column is which triangle you are. So this is like the dual. And then we can calculate all the boundary data from it. It takes 8 seconds more or less because it's algebraic instead of numerical. And from here, we directly obtain what I called beta tilde, which is up to a kappa to our real boundary data. But kappa we need to give it. So just given kappa, we obtain the Bij for our boundary data from here. I give this kappa according to a graph. This is just given by this. You can choose another kappa if you want. It doesn't matter. It's just a choice. And then after we have kappa, we can calculate back what is our boundary data, which is theta phi and k. And the group element we already solved from here. And the final step, of course, is to check what we given satisfies the equation motion we have. We have two equation motion. Remember, we have one closure condition, which is kappa multiply b multiply the area equal to 0. You can check this is satisfied such that summing over G gives you 0 finally. This is checked. And another check is to check the parallel transport equation, which now we have the SL2C solution. We have the BRG, which constructed exactly from the K I wrote before. So it's K tensor product K dagger minus 1/2 identity. And you can also check this is satisfied. So that's everything we need to have a calculation. There's homework. I don't want to do it here, but you can check it yourself to make you familiar a little bit with Python if you are not so. As we said last time, when we have a solution, we always have another solution which maps to GR minus 1 dagger. That's the cosine problem. When we're given certain BRG, we always have two solutions. You can check here. This G minus 1 dagger is also a solution. This is just a task, homework. If you're interested, you can do this. And finally, we output the theta and phi, which is the boundary data, the current state labels. Why we output it? Because later on, when we use the SLC form next package, we need the current state label. And this is the thing we built from our boundary data. So we just output it. You can output in any form you want. I just use the JSON form. OK. So now we finished the boundary data. Do you have any questions? I have one example which I write out the action. The idea is trivial. It's just write action using the analytic formula instead of numeric. And then we transform all these things into a function. This can be done in SymPy, but technically it's a bit complicated. So I suggest you read it. If you are interested, you read it afterwards. I don't need sim engine at the moment, sorry. Yeah, but this is just to make all the variables as a symbol and to insert our solutions. So this is basically build out the action so write out the action analytically, and then insert our boundary data and the solutions to it. You can give anything, and then test if it's really a solution to the thing by the first order derivatives and also second order derivatives, which is a Hessian. I don't want to talk it now, but I'll upload it and you can check it yourself. And this function can be directly, since it's SymPy, it can be directly transformed into the numerical thing, which admit all the variables as the input. And then you can do the complex critical point analysis. Given initial value, try to find the other. Given some initial value which is not a solution, for example, you can deform a little bit your boundary data, and then find another solution using the Newton method. I'll upload all this to the website, and you can do it by yourself. So as I said, these are the asymptotics analysis. You can also, now we have the action as a function. You can also do the using the Hongguang theorem, do the first order expansion in H bar, second order expansion in H bar. Any order as long as you can calculate. Of course, it's complicated because you have many variables. You have thousands of variables. If you have, for example, a large triangulation, not so large triangulation, but because each four simplex, we last time already estimate each four simplex has 44 variable without the spin. If we have spin, we have 54. So if we have 10, we already have hundreds of variables. That makes everything complicated, but it's calculable. And it can also be calculated pure analytically. And we don't need I mean, technically we use some truncation, we make some, but this position can be set arbitrarily large. That's why we use same engine and same pad to do the calculation. Okay. That's all I want to set for this part, and we can jump to the SL2C form next. I know many people also interested in this. Oh, I'm still doing some test run. One easiest way to, so okay. How many people are already familiar with compile things in Linux? 1, 2, 3. Okay. Actually, it's not so complicated. So the base code is in C, but now we have a Julia interface. But you still need to do the compilation yourself. I just write a shell script, which is very simple. If you're using Ubuntu, you can just call this shell script. It will do all the compilation, all the compiling things for you, and you get a usable code base afterwards. You can just run this. If you use, how many of you use Linux? Okay, yeah, at least more. If you use Windows, you can use WSL. I don't know if, yeah, Windows subsystem for Linux. That's the easiest option. If you use Mac, please use Docker. I think you can download it, the Docker for Mac. It's somehow like the virtualization machine of the thing to give you a Linux environment. And afterwards, you can directly call this. I think I can show you a test run. But since I already have everything, so this is trivial for me. No, I'm not in Ubuntu. Okay, I just want to do a test run, which I think I call it. So you just need to run bash, and this install SL2C form. You need the administrator because you may have some packages missing, so you need to install them. And then it will automatically download everything. I don't have internet, so it stops here. The internet is bad. But you can just run it. It will compile all the things it needed. Yeah, and download some other packages which will compile them first, and then compile the final SL2C form, and do the initialization. And then there is also a test run. You can run this is basically vertex amplitude, transition amplitude for the 10 spins, which is spin 1/2. This is two times the spin. And also the interturners also takes 1. This is 0, you know, because the interturner is 2, so no 0, 1 is 2 times the spin. But it's a test run. If there is no error appears, you are done. But this is only the C part. For the Julia part, you can run this. I'm not sure if it will work for you. You can do it by yourself. There is a no trivial thing. Julia is very easy to install. You just download it and extract it from the compressed file. The special thing is that you need to replace this pre-compiled, how do you call this? The dynamical library. Replace it with the system, the version in your system. Why we do this is because you know the C code is written with this is high precision library. The C code is written with the float 128, but now the Julia version is not compiled with it. That's why you need to replace it a little bit. And you can do this. Just find the the position wheel system library and make a link to the Julia one. It's simple. You can just read this. You can run this in your system. That's the only thing you need to do. And afterwards, you can run it in Julia. So if you download everything that is already this SL2C form folder, and it contains the Julia interface, and what you need to do is just run it. I can do a test run here. OK. And now this is just to initialize the library. So we set a email the parameter. You can set it to anything you want. We have a data folder. We already initialized it. Don't change the name. If you want to change the name, you need to reinitialize it. So this name is fixed. Or you copy it to other place. And then there is a configuration. This is just, as its name is, if we want to say something or not. Position, we always use very high position. And this one is how many, the largest, the maximum spins you want. You can set it if you have a lot of memory. And the final thing is, do we want to restrict the memory for each thread? We don't restrict. So this is the thing. And afterwards, we just initialize the library. And then we can do a real calculation. Let me change this. Because sometimes this need more time in your personal computer to run a large spin. So here is exactly the example I show you built from this boundary data. So we have 4 spins equal to 5, which is our equalator tetrahedron, and all the other spins of the triangle is set to be 2. So now here is very easy to give in. So we give all the spins. And these spins, there is a diagram. I can directly show you in the paper. So I don't want to draw it again. Should be, it's not this one, I think. Sorry, it's not this one. 22020434. Yeah. Now the internet works again. It's a keyboard diagram we already discussed during last lectures. Is this one. So you see how the spins and the arrows are oriented. So this we have kappa as +1 or -1. So if it's coming out, it's +1. Coming in is -1. This is the kappa. And this is the spins. This is how the spins arranged. And for this one, we have all the spins equal to 5. So this is our base tetrahedron. And for all the other spins is 2. And you just give out the spins and also the associated kappa to build the boundary data, boundary coherence state. If you don't want to build, if you only want to evaluate using the intertwiner, you can ignore all this. You just give the spins and the intertwiners, and then it will give you the result. And this is just a simple example. If I don't do this, I just give some spins. And now there is this 3. What is this 3? It's the cutoff we mentioned last time. So if you have enough computational resources, you can set a large cutoff. If you don't, you just set a lower cutoff. One thing is one can estimate a little bit because we know the 4 vertex amplitude is convergent. So this forms a convergent series. So in principle, you can estimate the error even you don't have the largest enough cutoff, but from the difference between different cutoffs, you can estimate the final convergence region. That's the thing. And you can find the details in these 2 papers. Here I can just run it, I think. Sometimes it's, let's do some tricks. Spins. You see it's very fast because I already run it. It will automatically catch every result you run. So this gives you all the, this gives you basically all the, because I only give the spins, I don't give the intertwiner. So this will give all the amplitude for all possible intertwiner. And A is the amplitude. You see it's a matrix. with all the interternal in all the interternal space. Why is 2, 2, 2? Because for each triangle, I think I write it here. This is the spins for each tetrahedron, and then you can estimate the dimension of the internal space. So for the first four, the dimension is 2. For the final one, the dimension is 11 because it's from 5 minus 5 to 5 plus 5. You have 11 interternals, and for this one, it's 2. So this is the 4 matrix of the amplitude. So if you only interested in the internal space, that's enough. But if you need more, then the coherent state. And now we load our data calculated from here, I just said. So I export this boundary coherent state, which I call it theta phi, into a file, and then I load it again. Rearrange it a little bit. It must be in this form, which is a 4x2 matrix for each tetrahedron. So why 4x2 is nothing else but each triangle we have corresponding to the area I just write. So we have 4 for each triangle, and each triangle we have 1 theta and 1 phi for the cosine. So this gives you all the boundary coherent state for the 5 tetrahedron, and each tetrahedron you have 4. And after you give this, you can just make a contraction. First of all, you need to calculate the coherent state, the expansion of the coherent state on the internal states. So this function does the trick. It's called coherent state compute. You write out let's delete the lambda, because I don't need lambda anymore. Well, lambda is just 1, 1. Okay. This is the spin, which gives you basically the internal states. And this is your coherent state label. And then this function just calculates how the value of the coherent state on each internal space. Sorry, I need to run this first. And you can check, for example, for the first tetrahedron. It takes some time. But for the first tetrahedron, it gives you the expansion of the coherent state on the internal space. There is some bug in the VS Code, so you always need to delete. I think I loaded half into this. Okay, doesn't matter. No. Somehow the kernel is down. I need to rerun it again. Okay, but let's continue. So this basically gives you the expansion of the coherent state on the internal space. And then what you finally need to do is to contract the coherent state with the vertex amplitude you calculated. And it's done in this thing. And finally, it gives you an amplitude for the coherent state. This is the thing. And you can calculate other things you want. It's just simple. Where I stopped? Yes. Yeah, now it works. Yeah. So this with the first is the first tetrahedron, and the amplitude gives you, because it's 2D internal space, this is basically how the coherent state expanded on the 2D internal space. This as the coupling, the expansion, the parameter. And then when you contract it with the vortex amplitude, it gives you, sorry, I changed the name. It gives you the final amplitude. And you can try with more complicated graphs if you want more, other boundary data, just use this tool. I will upload it. Yeah, up to now, do you have any questions or do you have anything you want to know? Yeah? Sorry?
Do you have MPI enabled on your machine to use multiple cores? Because when I try running from Julia, it crashes. So I had to change some initialization order.
Here, well, it has MKL and also MPI. It can be distributed in about everything. So for the Julia crash, I guess maybe, I don't know if you replace the hypervision library for Julia. If you don't replace it, it will directly crash Julia.
I can show you offline, but yeah.
Okay. But here I compiled, if you follow this procedure, it will be compiled with all the things you want. And also, here, if you know already some computer, this compilation, I use the BLAST system, which is a vectorization with the system one. You can replace it with the others you want, if you are familiar with this. This will boost a little bit of the contractions between tensors. Yeah, that's the thing. And also there is the GPU library you can load. You can load it not with SL2C form, but with SL2C form GPU. And then it will do all the tensor contractions in GPU. If you have a powerful one, you can try. But all the other things are similar. Yeah. Do you have any other thing you want to know? I guess just practice. That's the thing. Okay. Now we finally go to, we done all the spin-form stuff. Well, this symbol is still spin-forms, but now we need to have some simple examples. You can apply this to the action I just write. You compile it as a function, and then you can apply this symbol method to this action. But here I just do a very simple example with the array function. So this is Julia. We need some packages for Julia, and you can learn how to install them in Julia. It's very simple. The most important thing is the differential equations, which is a very nice library in Julia to solve the differential equation, to integrate out the differential equations. Let's check if I have everything available here. Again, I use SymPy to have some symbolic operations. So all this, you know, this Julia can call Python, Julia can call C, Python can call Julia, Python can call C, so you can call this in different languages, no problem. Okay. Now let's tell you something about the array function. It's a function that we know the asymptotic formula. And this is the form of the action. And basically, it's given by the amplitude is the integration of that with the exponential minus s. So we always start with something like this. And the action is just given by this. So we have one variable, which we already complexify it. The original integral domain is on the real line, if you want. And we have a, which is the parameter. I just define the function, and you already see this is a quadratic equation, quadratic action. Sorry, here is third. That's why we have over 3 typo. So third order, third power action, quadratic equation of motion. So we have 2 critical points. And one is at plus square root of minus a, another one is at minus square root of minus a. And we can also estimate the critical action. This is just let you know. And so we have 2 critical points. And now we can draw. Because it's 1D, you can simply draw all the faces and the real part of the action. And we know where is the critical point is here. So the below something lines is a line which is the constant phase line. So this is a constant phase contour. And this red line is the constant real part. And you can see here, so these 2 points are the critical points. One is plus and another one is minus. So A is 1, what I used. So A is 1 is minus R and plus I, if you want. But there's something more. If you look at, this is the original integration domain. It's convergent. But for these 2 critical points, the steepest descent line or the ascent line, one is convergent, another one is not. So you need to be careful. If you look at this, so S goes to infinity is convergent because I use exponential minus S. So the real part goes to infinity is a convergent thing. So this critical point is convergent if we follow in this steepest ascent line in this language. But this critical point is divergent. And from the Loops symbol or the steepest descent saddle point or approximation, you know, so if we deform the real line, since one is this, one is this, which one we deform it to? We deform it to the convergent one. This one does not contribute because it's already, this steepest descent lines already span the whole domain of the original real line. It's the same homotopy class, deformed from the convergent region to the convergent region. So even we have 2 complex critical points, only one is dominant. So we don't need to consider the other one. This is good. We don't need to consider the weight for the Loops symbols, or in other words, the weight for this one is automatically 0. So only one symbol contributes, which is this one. 1D is trivial somehow. Now we perform our Loops symbol method in this 1D example. If you remember, the Loops symbol is generated by the flow equation. So the critical point does not flow because it's a saddle point. It's a stationary point of the flow equation. And the flow equation, so we need something around the critical point to flow. So this gives our first approximation. And this V sigma is the region which around the critical point we let it flow. And we have another approximation is that, so the flow equation, if we want to flow to infinity, we need infinite time. Technically, we cannot do infinite time. So we also fix the time t. So these are the 2 approximations. One approximation is we do not consider critical point which do not flow. Which does not flow, we consider a region around the critical point to flow. So if it's very close to the critical point, it will give you the symbol very close to the original symbol we want to have. And then we fix t, so we only consider a subdomain of this line. Because it's exponential decay, okay. Yeah. Let's first. So we have last time we already discussed how to find this region around the critical point. We use the Hessian matrix, and this Hessian matrix is given by the eigenvalue of the Hessian matrix. You do it in the Takagi factorization, and we only consider the eigenvectors with the real eigenvalue, and then we have the flow of the Jacobi matrix as well, which transforms from the original z coordinate into the x coordinate we consider. And then we finally sampling in the x coordinate. So this transforms our original integration to an integration over x coordinate, and finally become a sampling problem where this f, the sampling, is going by the probability distribution on this exponential. And then you can do all the tricks. So what we need to do is, of course, solving this flow equation, which is the partial differential equation. And then we also solve this Jacobi flow equation. Here, everything for the Jacobi is trivial because you can show that the Jacobi equation can be solved directly by integration of the Hessian matrix. I mean, I can skip all this thing. What I want to show is we do a Markov-Monte Carlo method, as I said, so we have a probability distribution. And you just run the thing. What you get is exactly the same thing on this Lipschitz symbol. This is the approximated thing. And this is the weight, which is the original. So this is the distribution plotted using the probability distribution, and this is the sampling weight. We'll say they are very close to each other. Of course, I don't run a lot of points. If you run more points, it will be more close. So this is just a test that it converges very good. So for summary, you already see we do three things. First, we have the boundary data, and then we have the action, and we can evaluate the amplitude directly in the small spin regime, but also couple it to coherent state. So if you have a very powerful computer, you can also evaluate it into the large spin regime, which compared with the asymptotic expansion method with the action. But also you can do the Lipschitz symbol, which is in the intermediate regime for the large spin and small spin. You do the Lipschitz symbol to the action, and that's all the numerical tools you need to have, and you can do it at home. Just do some practice. Yeah.
Okay, thank you.